Conditional probability and its role in the probability theory. We will start with an explanation about the conditional probability, what is its definition and how we use it, and how Bayes' rule ties conditional probability to the total probability, and then we will go to examples on how to use Bayes' rule. Starting with the explanation of conditional probability. Conditional probability is the probability of a certain event given the occurrence of another event. So if we have, for example, two events, event A and event B, so we can calculate the probability of occurrence of event A on its own and the probability of occurrence of event B on its own. But what happens if we already know that event B occurs? So will that affect the probability or the uncertainty in event A? Of course it will, because knowing the occurrence of event A means that the occurrence of event B means that part of event A is now known, whether it happens or it doesn't happen, or at least we have additional information about event A. So the overall probability or the overall uncertainty of event A now is changed. The only case when the occurrence of B does not affect the occurrence of A, or the probability of A given that we know B is not any different from the probability of A, is when A and B are mutually exclusive. Because if you refer to this graphic, if we know event B, this has nothing to do with event A. So as a definition of the conditional probability or the relative probability, we can define the probability of A given that we know B, and this is the notation that we use, as the probability of the intersection of A and B divided by the probability of B. And of course this is only if B is a null event or non-phi event and its probability is not equal to 0. In general, if probability of B is larger than 0. So again, the probability of A given B is the probability of the intersection of A and B divided by the probability of B. Sometimes we prefer to write it this way, that the joint probability of A and B, this is the probability of A intersection B, is equal to the probability of A given B times the probability of B. So for example, if we want to know what is the probability of passing an exam given that I study well, the probability of passing an exam itself is a random event, random experiment. So there is some probability of passing the exam, and the complementary event is the probability of not passing an exam. But if we know that someone studied for that exam, so will the probability of passing the exam will be affected? Definitely it will be affected. So the probability of passing the exam given that that student prepared for the exam or studied the exam will be different from just the probability of passing an exam. So if we want to calculate the probability of passing an exam and studying for that exam, or the joint probability that I studied for the exam and I passed the exam, is the probability of passing the exam given that I studied for such exam. But this is only true if I studied for the exam. So we multiply by the probability of studying. So we can interpret the conditional probability in multiple ways. Either that the probability of A given B, and this is what we call the conditional probability, and it means that we are calculating the probability of event A given the occurrence of event B, and we calculated that as probability of the intersection of the two events A and B divided by the probability of B. Of course, the probability of B is fractional, as we said. The first axiom of the probability states that the probability of any event is between 0 and 1, and hence the probability of A given B will be larger than the probability of the intersection of A and B, larger than the probability of A intersection B. Another way to interpret it is that the probability of A intersection B, and this is what we call the joint probability, because the intersection of two events means the occurrence of two events. So the joint probability of two events, the probability that two events happen, is the probability of one of them happens given the other times the probability of occurrence of the other. And consequently, we can, by similarity, we can write it as the probability of B given A times the probability of occurrence of event A. In other words, we can write the probability of B given A, as we have defined here the probability of A given B. We can define the probability of B given A as the probability of the intersection of A and B divided by the probability of A. So again, we can interpret it in these two different ways. This expression is sometimes referred to as the multiplicative rule, where the probability of the intersection of two events is the multiplication of the marginal probability, this is the probability of a single event, times the conditional probability, which is the probability of a certain event given the other event. And this can lead us to Bayes' rule. So let's define first Bayes' rule and then see how can we interpret such rule. So Bayes' rule has to do with what we call the law of total probability. Law of total probability. Let's assume that we have a random experiment and this is our sample space, and this sample space is composed of mutually exclusive events. For example, event B1, event B2, event B3, and event B4. So as we can see, there is no intersection between these four events. So these four events are mutually exclusive. And let's assume, or let's define event A, which has some parts in intersection with event B, some parts in intersection with event B3, some parts in intersection with event B2, and finally some parts in intersection with event B1. So if we want to calculate the total probability of event A, so this is event A, so the total probability of event A is equal to the probability that event A occurs given that event B1 occurs multiplied by the probability of occurrence of event B1 plus the probability that A occurs given B1 is known times the probability of occurrence of B2, and so on for the other two mutually exclusive sets B3 and B4. So this is what we call the law of total probability. So the probability of event A is the summation of the probability of this part, and the probability of this part is the probability of A given that we are within the knowledge space of event B, in addition to the probability of this part, which is the probability of occurrence of A given that we are in knowledge of event B 3. This is the same for probability of event A given that B2 is known, and finally this part is probability of A given that B1 is known. So this is the rule of total probability, and hence if we want to calculate any of the conditional probabilities, for example the probability of B1 given BA, now let's assume that we know something about event A, we know about the occurrence of event A. So what will be the probability of B1 given A? From the rules that we just mentioned, it is the probability of the intersection between B1 and A divided by the probability of A. So this is what we call the Bayes rule, where probability of A can be calculated this way. The same exact rule if we want to calculate probability of B2 given A, so it will be the probability of B2 intersection A divided by the probability of A, which is calculated up there. And what about the probability of B1 or B2 or B3 intersection A? It will be, let's calculate B1 intersection A. It will be again from the conditional rule probabilities that we mentioned. It will be probability of A given B1 times the probability of occurrence of B1. So this is what we call Bayes rule. So this is Bayes rule, and it is calculated using the conditional probability, the definition of conditional probability, and the law of total probability. We better understand the conditional probability and Bayes rule through an example. So let's switch to our example. Our first example will be as follows. Let 2 items be chosen at random from a lot containing 12 items, of which 4 are defective. So we have a lot or a set of 12 items, 4 of them are defective. So let's summarize our givens. So we have 4 defective items, and consequently the remaining 8 items are not defective, or let's assume they are good items. And we choose 2 items out of those 12 at random. And we want to find the probability that the 2 parts are defective, the probability that exactly 1 part is defective, and the probability that the first part is defective given that the second one is defective. So obviously this last requirement is the one in which we will use the conditional probability. So let's calculate the first two ones because they are easier ones. What is the probability that the 2 parts are defective? There are many ways to calculate this probability. One of them is using the counting techniques that we studied before. So first of all, we want to calculate probability. So we need to find the total number of ways of selecting 2 items out of the 12, and this will be the denominator of our probability. And for each of the other of the required cases, we calculate the probability or the number of ways of having the described items, and then we divide these 2 numbers to get the probability of occurrence of the event. So what is the number of total ways to find or to select 2 items out of 12? So that will be 12C2. So, and again here we used the combination way of choosing 2 out of 12 because the order doesn't matter. We select 2 items, so it doesn't matter whether the first one we chose is any of the items. So different arrangements are counted as a single combination. So this is the total number of ways we choose 2 out of 12. And we want to calculate the number of ways that the two parts are defective. So there is, in order to choose two of which two are defective, so we have out of the 4 defective items we want to choose 2, and out of the 8 good items we will be choosing 0 items. And again here we applied a multiplicative rule such that the total number of ways to choose 2 defective parts is that those 2 are chosen from the 4 defective components and 0 are chosen from 8. Of course this number is equal to 1, so we can just drop it. However, it's better to write it so that to reflect our understanding of the problem, and the probability itself will be that number divided by the total number of possible ways, 12C2. Let's write this, make this calculation, because we will use it right now to verify the other way of solution that we will present. So 4C2 is calculated as 4 times 3 over 2 times 1, and 12C2 is 12 times 11 divided by 2 times 1. So we can cancel these terms with these terms, and we'll be left with 4 over 12 times 3 over 11. The other way to think of this, the solution of this part, is to create a tree of the possible ways of selecting the 2 items. So first, let's assume we have a pool of the 12 items, and this pool has 4 defective items and 8 good items. So to choose the first one, or the first item, it can be either good, so the first item is good, or it can be defective. What is the probability of choosing good item from those 12 items? Right, we have overall 12 items, 8 of them are good, so we have a probability of 2 over 3, while the probability of choosing defective item is 4 divided by 12, or 1 over 3. That's good. Now, if the first item is a good item, what will be the status of the pool of items? Now, the good items are decremented by 1, so we have only 7 good items, while the defective items are still 4 as they are. Same here, the pool will change such that we are left with 3 defective items, yet we still have 4 good items. Now for the second selected item, again we go to each terminating branch of this tree and we check all the possibilities. So if the first item is good, the second item can be again either good or defective, and if the first item is defective, the second item can be either good or defective. And again, what will be the probability of having a good as the second item is good, but now given that the first item was good? Because as you can see, knowing the first item affects our knowledge of the status of the pool or the lot of items that exist, and consequently the probability of having good item in this case will be different than finding a good item in the second case. In this case, the probability will be equal to 7 out of 11, while here the probability of having good item will be 8 out of those 11. So this 7 over 11 is the probability of having the second item good, given that the first item is good. And this number here is the probability of having the second item is good given that the first item was defective. So if you want to calculate the probability that the two parts are defective, so this is the probability that the first one is defective intersection that the second one is defective. So it's probability of D1 intersection with D2. So here if we apply the conditional probability, it will be the probability that the second is defective given the first is defective times the probability that the first is already defective. So this is the probability that we want to calculate. Probability of D2 given that the first is defective is, here we will have 3 possibilities out of 11, so it will be 3 divided by 11. So if we substitute back here, it will be 3 divided by 11 times the probability that the first is defective, and this is the value that we calculated here, equal to 4 divided by 12. Of course, if you compare this value here with the value that we got using the first method, it will be exactly the same value. It's 3 divided by 11 times 4 times 12. So we can either calculate it using the conditional probability concept that we just explained, or we still can use the accounting techniques as we explained in previous lectures to calculate the required probability. Let's now calculate the second part, or the second requirement of this question. It asks for the probability of having exactly one part defective. So to have exactly one part defective, that part can be either the first part or the second part. So we can here apply Bayes' rule and the rule of total probability, that we want to calculate the probability that exactly one part is defective, but this part can be either the first part or the second part. So we can calculate this as the probability that the first part is defective, but if the first part is defective, then we need to make sure that the second part is good, so that exactly one part is defective. So this is one possibility. And another possibility, so we have addition rule, is that the first part is not defective, it's good, in which case, in order to be included in the required probability, that means that the second part is defective. So we want to calculate the probability that either the first part is defective or the second part is the defective one. Again, for each one of these two terms, we can refer to the conditional probability. So this is the probability that the second is good given the first is defective times probability that the first is defective, plus here probability that the second one is defective given the first is good times the probability that the first one is good. Again, referring to the tree that we just erased, that will be equal to the probability that the second is good given the first one is defective. So that is and the probability that the first one is defective is, and similarly we calculate the probability that the second one is defective given the first one is good times the probability that the first one is good. Now for the third requirement, or the third part of the question, we want to calculate what is the probability that the first part is defective given that the second one is defective. So what is the probability that the first one is defective given that the second one is defective? So again, using the conditional probability, this is the probability that both of them are defective. So probability of D1 intersection D2 divided by the probability that the second one is defective. So this is the event that we assume knowledge of, the probability of D2. Again, probability of D2 can be calculated using the rule of total probability, and the probability of the intersection can be found or can be calculated as we calculated in the first part, that the two parts are defective. So this is the numerator is what we calculated in part A, and the probability that the second item is defective can be calculated using the rule of total probability. Let's calculate this one together. So from our tree, so let's put it together again. So we have 4 defective, 8 good. If we get the first one defective or the first one good, the pool now changes. It becomes 3 defective, 8 good. Here it will be 4 defective, 7 good. And then we can get the second item is either defective or good, and here the second item is either defective or good. So the probability of having a second defective items is the probability of having a second item defective given the first was defective, multiplied by the probability that the first one is truly defective, or that's why we have plus the probability that the second item is defective given the first one is good times the probability that the first one is good. Again, this is the application of law of total probability, where what are the cases of having the second item defective? It is either this case or this case. This case is identified as the probability of having the second item defective given that the first one is defective, multiplied by the chances that the first one is really defective. And this possibility is the probability of having the second item defective given the first one is good under condition, or multiplied by the probability that the first one is good. So again, to calculate by numbers, probability of second one is defective given the first one is defective is 3 divided by 11 times this probability is 4 out of 12 plus probability that the second one is defective is 4 divided by 11 times the chances that the first one is good, which is 8 divided by 12. So this is the probability that the second item is defective. Once we substitute it here in the denominator and we get the numerator from part A, we get the probability required in part C. Let's move to the next example. We have a coin which is biased so that a head is twice as likely to occur as tail. So we have a coin in which the probability of head is not equal to the probability of tail. Instead, the probability of head equal twice the probability of tail. And of course, we know that the outcomes of such random experiments in which we flip a coin is either head or tail. So the probability of such sample space is equal to 1. So we know that probability of occurrence of head plus probability of occurrence of tail equals to 1. So we can think of it as this is either the probability of the overall sample space, so it should be equal to 1, or head and tail are two mutually exclusive events. So the probability of their union is equal to the summation of their probabilities, and their union equals the sample space, so their summation of probabilities equal to 1. Using these two equations, we can conclude that probability of head is equals 2 over 3, while the probability of tail is equal to 1 over 3. So these are just preparations for what will come next. It asks what is the probability that two heads appear in 3 tosses. So if we toss the coin, or we flip the coin 3 times, what is the probability that 2 heads appear? And again, these 2 heads are not necessarily the first and the second. They can be the second and the third. They can be any 2 of the 3 tosses. So how would we think of such a problem? Again, the total number of possibilities of the 3 tosses, they are 2 possibilities power 3, 2 times 2 times 2. So these are the total number of possibilities. And in order to have 2 heads out of the 3, so this can be any of the 3 tosses. So we have 3C2. And in order to calculate the probability, it will be 3C2 divided by 2 power 3. So this is, again, this is a very simple part of the question related to knowing what is probability meant. So again, it is the number of outcomes, or the number of ways an event can occur, divided by the total number of ways a sample space occurs, and how to calculate or how to count the number of occurrences of a certain event. Now, for the second part, part B, it asks what is the probability that the first head appears on the 7th toss. So that means that we toss the coin once and we don't get a head. We toss it again and we don't get head. We toss it a third time and we don't get head, and so on until the 7th time we get a head. So in order to calculate such a probability, each of the subsequent events tossing the coin is independent of the outcome of the previous toss. So if we apply the rule of conditional probability, we can say that this is the probability that we get head in the 7th toss, given that it was head in, given that it was not head in the previous toss, so it was tail in the 6th toss, times the probability of having tail in the 6th toss. And when we get to the probability of having tail here, again we have the probability of having tail in the 6th toss, given that in the 5th toss, or the preceding toss, it was also tail, because again it asks here about the probability of having the first head appearing in the 7th toss. So by cascaded conditional probability, we can calculate it as the probability of having head in the 7th toss, given it was previously tail, and this one given that the 5th was tail, and so on until the probability that the first toss is tail. And because the events are independent, so knowing that or having that 4th toss, for example, was tail, has no influence on the outcome of the 5th toss. So we can safely consider that the probability that the 6th toss is tail, given that the 5th toss is tail, is the same as the probability that the 5th toss is tail. And similarly, the probability that the 5th toss is tail, given the previous one was tail, has nothing to do with knowing about the previous one. Similarly, the probability of having the 7th toss head is not dependent of having the previous one tail or head. And then we can calculate that probability of having a head in the 7th toss is 2 over 3, and this one is 1 over 3 multiplied by 1 over 3 for 6 times, so it is 1 over 3 power 6. So this is the probability of having tail, 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 and finally the 7th one is head. Of course, this is a problem that we could have solved without any prior knowledge about conditional probability. However, we wanted to use the concept of conditional probability here to relate to the possible ways of solving a certain problem. For the last part, or the last requirements, it asks what is the probability that the third head appears on the fifth toss. So again, that can be thought of via our understanding of the way we solved the previous two parts. So in order to have the third head in the fifth toss, that means that in the previous four tosses, two of them were heads. So we can calculate such a probability as the probability that the fifth toss is head, which is again independent of any previous tosses. So this is the probability that we have head in the fifth toss, multiplied by the probability of having two heads in four tosses. So again, probability of having head in the fifth toss is 2 divided by 3 times probability of having two heads in four tosses, means that we have two heads, so that is probability of head times the probability of head, and the remaining are probability of tail times the probability of tail. However, how many ways are there to have such probability? How many ways that two out of those probabilities are two out of those four tosses are head? This can be first and second, second and third, first and fourth. So we have out of those four, any two can be heads. So we have a number of ways for C2. Each one of those ways has this probability, is that we have two heads times two tails. Again here, just to make sure that we understand the first part correctly, we want to calculate what is the probability that two heads appear in three tosses. So what we calculated here was the probability of the occurrence of such event, that we have out of three tosses, two of them are heads, but here we forgot to consider the probability of having a head versus the probability of having a tail. So in order to calculate it correctly, we have to consider the fact that the coin is not unbiased, instead it is biased. So in order to have two heads appear in three tosses, so we have the probability of having a head times the probability of having head times the probability of having a tail. So this is the probability that two of them are heads and consequently one is tail, but this probability happens for more than one case. This happens when the first two are heads, or the last two are heads, or the first and the last one are heads. So there are three C2 ways that this can happen. Again, here we are using multiplicative rule to calculate the probability of a certain event, and to take into consideration the different orders that this event can occur, we use the additive rule. So we have to calculate this probability plus a similar one for a number of times equals 3C2. So because all the probabilities are similar, so instead of just adding them 3C2 times, we multiply such a probability by 3C2. Our next example will be a straightforward application to Bayes' rule. So the example says the probability that a medical test used for detecting a certain illness correctly identifies someone with illness as positive is 0.99, and the probability that the test correctly identifies someone without illness as negative is 0.95. The incidence of illness in general population is 1%. A person then is selected at random from a population and takes the test. If the result is positive, what is the probability that this person is indeed ill? So again, of course, if the result is positive, that does not mean 100% that the person is ill, because there is a chance of false positive test results, and there is a chance of false negative test results. In order to solve this problem, we have to understand the wording of the problem correctly, and then map it to meaningful events, so that we can define what is the required probability. So let's assume that we have event A, and this event A is the event that a person is ill, and we know from the problem that probability of A, which is now the probability of illness, is given by this sentence. The incidence of illness in general population is 0.01, so the probability that someone is ill in the general population is 0.01. So this is event A, and this is what we know about it from the given. And then event B, let's define it as the event B is that the test result is positive. However, we are not given the probability of test results. We have not made a study about a large number of tests and counted how many of them are positive to calculate the probability of test results. Instead, we have the following probabilities. We have the probability that we have positive result in case someone is ill. How do we know this? Let's read the first sentence again. It says that the probability that the medical test used for detecting a certain illness correctly, so that means that we are making a test for someone who is correctly ill, identifies that one with illness as positive. So this is the probability of positive result given that a person is ill. So in our notation, it's the probability that P occurs given that A occurs. So this is the 0.99 probability. Okay, let's do the second one. It is the probability that the test correctly identifies someone without illness. So it is probability of someone without illness. So he is not ill. So ill complementary as negative. So probability of negative result given that the person is not ill. So this is the probability of the complementary of B given the complementary of A, and we know it is 0.95. Now the required is to find the probability that a person selected from random and takes test that the test result is positive. Sorry, that if the test result is positive, so if the test result is positive, so given that it is positive, what is the probability that the person is indeed ill? So what is the probability of illness given the test result is positive? So again, this is probability of being ill, so that's probability of A given B. Of course, there is a huge difference between the required and this given. This given is the probability that someone is ill, so we know he is ill, and we calculate the probability that the test result is positive. The required probability is completely different. It is the probability that given that we know or we observe or it becomes certain that the test result is positive, what is the probability that the person is ill? So again, this is a direct application of Bayes' rule. So we can say that probability of A given B is equal to probability of A intersection B given probability of B. and then probability of A intersection B can be written in terms of the conditional probability. So it is probability of B given A times the probability of A. Luckily we have probability of A as 0.01 and probability of B given A, that's 0.99, and then for probability of B we calculated using the law of total probability. So probability of B equals probability of B given A times the probability of A plus probability of B given the complementary of A times the probability of complementary of A. So this is the remaining set. So again, probability of B given A is known, probability of A is known. What is the probability of A given, sorry, what is the probability of A complementary? It's 1 minus probability of A, and the probability of B given A complementary we can calculate it from this given, that it is 1 minus probability of B complementary given A complementary. So again, substituting with the known numbers, we can calculate the marginal probability B of P, and we know the numerator here, and consequently we can calculate the required probability. Our last example is as follows. In a particular production run of semiconductor manufacturing process, 20% of the chips directed to high level of contamination, 30% to medium level, and the rest low level contamination. Let's straightforward translate that into expressions. So probability of high level of contamination is 20%, probability of medium level of contamination 30%, and the rest is low, which is the rest of the complete 100, that is 50%. Then experience indicates that chips with high level of contamination fail with a probability of 0.1. So that is what is this is the probability of failing given that it is highly contaminated. So this is 0.1. Those with medium level fail with a probability of 0.1. So given that it is medium level, the probability of failure is 0.01, and those with low level, so the probability of failure given there is low level of contamination is 0.001. So it won't, the requirement is to calculate first what is the probability that a randomly selected chip fails. So again, this is direct application for rule of total probability. So it's probability that it failed given it was highly contaminated times the chances that it was highly contaminated, plus the same for low level and the same for medium level. So we are given those three marginal probabilities and those three conditional probabilities, and we can calculate them. The other requirement will be what is the probability that one chip was highly contaminated. So what is the probability it was highly contaminated given we observed that it failed. So again, this is direct application for rule of total probability. So here will be probability of failing in the numerator, which we just calculated, and here it will be the probability of failure given high contamination times probability of high contamination, which can be calculated directly from the givens. So again, this is a straightforward application for the Bayes rule and the conditional probability, as well as the law of total probability. One last note that we would like to mention here it's related to independent events. As we mentioned in an earlier example, independent events are events that do not depend on each other, and consequently the knowledge of one of them does not affect the knowledge of the other. So if we have two independent events, then the probability of occurrence of one event given the knowledge of the other event is not affected by such knowledge. So we can write it as probability of B given A equals probability of B, and similarly probability of A given B is exactly probability of A without being affected. So this is true in case of the events are independent, and consequently in this case, if we want to calculate probability of A intersection B, so in general that is probability of A given B times the probability of B, and if they are independent then probability of A given B is just the probability of A, and we get to this very useful relation which states that if two events are independent, then the probability of their intersection is the product of their marginal probabilities. So the probability of A intersection B is the probability of A times the probability of B.